Hello, my name's Charlie House and I'm talking to you today about some work I've been doing investigating the effect of uncertainty on active acoustic cloaking. This work was done at the Institute of Sound and Vibration Research at the University of Southampton, supervised by Dr. Jordan Cheer and Professor Steve Daly, and is funded by BAE Systems and the EPSRC. I'm going to start off talking about what active acoustic cloaking is and why we might want to do it, before moving on to looking at the robustness. Acoustic scattering describes the interaction between an object and a sound field. This could be an architectural pillar in a concert hall, for example, interfering with the sound field generated by the PA system. As the sound waves travel from the PA system through the space, they hit the pillar and bounce off. You get a scattered field. Any audience member sat nearby will hear the direct sound from the PA system and the reflected sound from the pillar. This will reduce the intelligibility and the audio quality. For this and other reasons, there's an interest in reducing the effects of acoustic scattering, such that the sound field is identical whether the scattering object is there or not. Active control is a common method to reduce unwanted sound and vibration in a variety of situations, and would be a good way to acoustically cloak an object. We could design an active control system to use an array of sensors to detect the scattered acoustic field, and an array of loudspeakers to cancel it out. If the scattered pressure can be forced to zero, the object will be effectively cloaked, and will therefore not interact with the sound field it's placed in. The problem with this is that any sensor in a sound field measures the total pressure, P tops, you can see in this image here. This is the summation of the incident pressure, the noise from our PA system, and the scattered pressure, the reflections from the pillar. An active control system would require a measurement of P scat, as that's what we intend to minimise. However, it's not possible to directly measure this without the measurement also containing the incident field. Various methods have been presented in the literature to take this total pressure measurement and decompose it into its incident and scatter components, the scatter component of which can then be taken off to form the disturbance signal for an active control system. These include virtual sensing, analytical or numerical modelling, or wave decomposition. Each of these systems requires a setup phase, where various acoustic transfer responses are either measured or modelled, which allow this real-time measurement of total pressure to be broken down into its incident and scatter components. As a result of this setup phase, these algorithms have the acoustic properties of the system baked in or hard-coded to the root of their operation, and therefore if the physical system was to change even by a small amount, the entire scattered pressure detection algorithm breaks down, and therefore the controller stops working. This presentation will present an investigation into the robustness of an active acoustic cloaking system to variations in the scattering object. We'll look at how quickly the acoustic cloaking performance deteriorates when the scattering object is perturbed. To allow for this investigation, we will consider a system consisting of a rigid spherical scattering object. This will be surrounded by 16 dual layer sources, which will be used by the controller to minimise the scattering. Each source consists of a pair of loudspeakers, one pointing radially in and one radially out. This allows us to control the near field and the far field of the scattering object. We'll surround this by an array of 40 far field pressure microphones. These will be used to detect the scattering, and will excite the system with an instant acoustic wave. This is the noise from our PA system, if you like, which travels through space and it hits our scattering object, in this case a sphere. Sound waves bounce off, which are measured by the red microphone array and then minimised by the loudspeakers. To allow for an investigation into the effects of uncertainty, we're going to look at this with three different size spheres. The nominal case, the middle one, has a radius of 0.15 metres, but will then increase the radius to 0.25 metres and decrease it to 0.11 metres. To see what happens when the system is changed. Here are some photographs showing the experimental setup which corresponds to this system. We have large plaster spheres acting as our scattering objects, surrounded by rings of loudspeakers and rings of microphones, as discussed previously. This was all set up in the anechoic chamber in the ISVR, with a far field loudspeaker providing the incident acoustic wave. Using this setup, we measured a number of acoustic responses, between each control source and each microphone to form the matrix of plant responses G, and between the primary loudspeaker and the microphones to form the vector of disturbance signals D. Doing this with and without the sphere present and subtracting the two sets of responses allows us to calculate the scattered pressure at each microphone position, which we then design the controller to minimise. In this study, we're using an optimal harmonic controller formulated in the frequency domain. This can be considered the best case scenario, as it neglects practical constraints such as reference signals and causality, and therefore, whilst it's not directly implementable, it allows an investigation into the effects of uncertainty without overcomplicating the controller design. In the nominal case, the scattered pressure at each microphone and at each frequency can be expressed as the difference between the total and incident pressures. The error after control can be expressed as the disturbance plus the contribution from the control sources, given by the matrix of plant responses G multiplied by the vector of control source strength U. In this control strategy, the controller aims to minimise the sum of the squared scattered pressures at the far-field microphone array, which, as detailed in the literature, results in a formulation for the optimal control source strengths as this. This plus beta I term included here is Tikhonov regularization, included to constrain the magnitude of the source strengths and to increase the robustness and reduce the conditioning of the problem, but we'll touch on this in a little bit more detail a bit later on. We do all this for the nominal case, and then we perturb the system and see how well those optimal source strengths work with a different system. By changing the size of the sphere, we're effectively adding some uncertainty, delta ds, to the disturbance field and to the plant response, which in turn results in a different error in the control system. This plot shows the performance of the active control system. The left-hand image is the nominal case, whilst the two right-hand images are the two perturbed cases. The colour scale is attenuation in the scatter sound power, with dark blues it being 0 or negative attenuation, and deep red being 10 dB. In each case, frequency is on the x-axis, and the value of this beta term, this regularization parameter, is on the y-axis. You can see up at the top of these plots, when we regularize to a value of beta is 10 to the 2, we get 0 attenuation in every case, whether we have the nominal sphere or the perturbed spheres. This is because we're over-regularizing and over-constraining the source strengths, which results in the controller just turning them off. At the opposite end of this plot, down at beta is 10 to the minus 10, if we under-regularize, we do very well in the nominal case, but very poorly in the perturbed cases. In this middle region is where things start to get interesting, where the nominal case kind of does okay, and the two perturbed cases also kind of do okay, and this is kind of where we want to be aiming for a robust system. To view this in a little bit more detail, we can look at the difference between these, so the large sphere minus the nominal sphere, or the small sphere minus the nominal sphere. This shows us the effect of uncertainty on the performance, and can be considered as the reduction in the acoustic cloaking performance, presented here, again over frequency and values of beta. In these plots, a deep red shows 0 dB difference, so the controller works equally well whether we have the nominal sphere or the perturbed spheres, and a deep blue shows that we're losing 30 dB of performance by changing the system. Again, when we over-regularize up at the top of these plots, we have 0 change. The controller does nothing, whether it's with the nominal case or with the perturbed cases. When we under-regularize, we start to see this large decrease in performance, especially at lower frequency. This can be explained by the condition number of the system. As you see in this equation at the bottom, we have to invert the matrix GHG plus beta I to calculate our optimal source strengths. The condition number of this is defined as the ratio of the largest to the smallest eigenvalues of this matrix, and it defines how stable the inversion is. A large condition number will result in a less stable inversion and give you a system where a small change in the input parameters results in a very large change in the output parameters. This is plotted in the right-hand plot here, again over beta and frequency. This plot clearly shows that in the bottom left corner, where we have low frequencies and low values of regularization, we have a very high condition number, and therefore a poorly conditioned problem. This decreases when you go up in beta or up in frequency. This corresponds well to the plots on the left-hand side, where you can see that a large condition number on the right-hand plot results in poor robustness in the left-hand plot. Therefore, the value of regularization is clearly key to the system. If we over-regularize, we get a very robust performance across all the perturbations, but a poor performance in each case. If we under-regularize, we do well in the nominal case, but poorly in the perturbed cases. To view this in more detail, we can look at the broadband attenuation performance across the controller for each value of regularization, plotted here. Here, the blue line is the nominal case, and the two other solid lines are the two perturbed cases. The y-axis is the broadband attenuation in the scatter sound power, and the x-axis is the value of regularization used. This plot clearly shows that at the right-hand side, again, when we over-regularize, the controller has 0 effect in every case. On the left-hand side, when we under-regularize, we do very well in the nominal case, but quite poorly in either of the two perturbed cases. As we transition between these two regions, the performance of the nominal sphere decreases, whilst the performance of the two perturbed systems increases to a maxima before falling off down to 0 at higher values of regularization. This is the region we want to be regularizing our system to be in, if we want to ensure robustness. To do this, we can average these three lines, which is plotted as the dashed line here, and this can be considered a robust performance. If we can regularise to be at the peak of that dashed line, we will do the best we can for any sphere ranging in size between the largest and the smallest cases we've considered. If we take this value of regularisation and look at the performance over frequency, you see this. For reference, on this trade-off plot, we're taking this point here. On this plot, you can see that the dark blue line is the nominal case, and again, the two other solid lines are the two perturbed cases. For reference, the dashed blue line is the unregularised nominal case. This is the performance that could be achieved if we didn't care about regularisation. This plot shows that by regularising, we're losing a lot of performance in the nominal case, especially at lower frequency, where the system is poorly conditioned. However, by doing this, we're heavily increasing our robustness. And actually, now the controller performs almost equivalently, whether we look at the nominal case or the small sphere. Even in the case of the large sphere, which is not doing quite so well, we're still achieving control across the majority of the frequency range, albeit at the expense of the nominal performance. Clearly, for a practical system, you would need to set your regularisation value based on your required nominal performance and the error limits on your measurements. If you know there will be uncertainty in your system, you should regularise to a higher level and accept the hit in the nominal performance. If you're confident your system will not change, you can regularise it lower and do well in the nominal case, but at the risk that if anything does change, the system will not be robust to it. To conclude, a practical active acoustic cloaking system requires additional processing methods to estimate the scattered pressure. These methods use measured or modelled transfer functions, which can vary over time, therefore leading to a problem with robustness. We've investigated the effect of robustness on active acoustic cloaking using measured data corresponding to a rigid spherical scattering object. The presented system can achieve up to 19 dB of attenuation in the scattered acoustic power in the nominal case, when robustness is not considered. If we perturb the system by increasing the radius of the spheres by 66% or reducing it by 26%, the performance reduces. We've investigated the trade-off between the nominal performance and robustness by varying the value of regularisation, and we've shown that a robust solution can be achieved, which can achieve up to 7 dB attenuation in the scattered acoustic power for the nominal case, almost this for the small case, and some levels of attenuation in the large case. Thank you very much for listening. I'm not entirely sure how this is all going to work, but please do drop me an email if you have any questions or comments on the paper. Thank you.